Hi everybody, my name is Carl Schultz. I'm from the University of Texas, which is in Austin, and I'm here today to talk about OpenHPC and talk about it as a community project to provide building blocks for high-performance computing. So I thought I'd give you a quick overview of our project if you have not heard anything about OpenHPC. So OpenHPC is a collaborative project that's organized through the Linux Foundation. I'll show you the members who are involved in a second, but it's basically an international community of people who are all coming together to work on providing an open source HPC stack. In terms of our membership, we have a collection of folks from academia, industry, and national labs. And really the reason for the creation of OpenHPC is that we all had a common interest in HPC software and system management. And I should say that by background, I spent about a decade, a little closer. It's going to get very loud. Better? Okay. I spent about a decade at an academic supercomputing facility in the US, and one of the things that we spent a lot of time on supporting a large user group was we had to build a lot of open source software over and over. And so one of the motivations for creating something like OpenHPC was to try to hopefully minimize that duplicated effort and put it together in a community project. So this was really created by a desire to have this open effort to more efficiently build is one thing, but more importantly to test and deliver integrated HPC software, components, and tools. So see, now we're too close. It's okay? Yeah? The project was actually formalized back in June 2016, so a relatively new project, but we have been around for a few years, and I'll show you our membership here in just a second. But let me tell you a little bit about the project mission and vision. So really, these are our mission and vision statements that really what we're trying to do is provide a reference collection of open source HPC software, with the idea being that we're lowering barriers to deployment, advancement, and use of modern HPC tools. And the thing to try to highlight here is that we're trying to bring together basically different points of view from the HPC community. So that includes users, and I'm sort of an application user by training. My background is in aerospace engineering, so I sort of grew up doing HPC because I was a consumer of HPC resources. So I'm sort of in this group here, but I've also done others, but trying to combine users, developers, researchers, and also people who are standing up big HPC systems, so administrators, so folks like supercomputing centers who are building big systems, and also the people who are supplying those systems, so vendors as well. So that's really the idea, is to try to bring all these folks together, and try to reduce the duplication of effort in terms of building open source software. So here's sort of our collection of partners today who are all formally part of the Linux Foundation project. Obviously, SUSE is an important member. SUSE was actually a founding member of the OpenHPC project. They've been there from the beginning, and we actually take advantage of a lot of SUSE products to help support and actually deliver the OpenHPC releases. So we use the Open Build service, which is an open source tool that we actually use to build all of the packages that come out of OpenHPC. But you will notice this is a mixture of academics, labs, and industry, and that sort of goes back to our motivation for trying to put together a community that brings all these different folks together. So it's folks who are providing HPC systems, it's people who are providing HPC software, it's integrators, and you'll also notice multiple OS vendors here as well, and a lot of academics. To be fair, we have a lot of academic usage by OpenHPC because it's all open source and there's no charge associated with it, which as academics, and I'm in academia, that's our favorite cost. Free is the best cost possible. So usually when I give sort of an introductory talk to OpenHPC, I like to just highlight a couple of few takeaways. So if you just remember one or two things about OpenHPC, hopefully these will be things that resonate with you. So in terms of our architecture, what we're trying to target is just a very familiar cluster architecture, things that you would expect if you're standing up an HPC system. So in this case, I'm talking about bare metal, but obviously, we'll see in a second that OpenHPC is really a software repository, so you don't necessarily have to use it on your own resources that are on site. You can also use it on cloud resources. But this particular architecture is highlighting the usage from a bare metal perspective. So what we sort of expect is that you have, one head node and some number of compute nodes. And this you would install your favorite operating system. And obviously your favorite operating system in this case is going to be SLES. And you would install that on this head node. And then you could use components that come from OpenHPC to basically provision the rest of the system. from a hardware perspective, things that we sort of assume you have is we assume you have some sort of management network. That would be an Ethernet interface that's highlighted in green. We assume you have some sort of out-of-band network. So for example, a BMC interface so that you could do IPMI, so you could remotely power things on and off. And while initially when we first came out with OpenHPC, we assumed that you had some sort of high-speed interconnect. So whether that be InfiniBand or OmniPath, something like that. We sort of relaxed that a bit, but a lot of our HPC users obviously have some sort of high-speed interconnect. And if that's the case, this would be sort of your communication layer for your application, doing MPI over that. Or also, if you have the use of a parallel file system, then you would do that over the high-speed interconnect as well. So today, the two high-speed parallel file systems that we support from a client perspective are Lustre and BGFS. And I should say, we got more folks here. If you have questions along the way, please feel free to ask me. We're all friends here, so yeah.
You were saying that you natively support Lustre and BGFS?
That's right.
Okay.
Yeah, but this is on the client side. So if you were to go download OpenHPC recipes, what you would see is that we document how to enable the client side of that. We don't go through how you set up the server side of that because it's sort of very sensitive to hardware. But on the client side, we do. Yep. So this is high level from the architecture point of view. I will say if you were to go access the OpenHPC recipes, we sort of focus on this head node and these compute nodes, but obviously in a large HPC installation, you're going to have some management infrastructure as well. We provide some provisioning capability, and it would certainly be quite reasonable to use that to stand up one or more login nodes, one or more administrative nodes. You have all the tools at your disposal to be able to do that as well. All right, so that's one key takeaway from the architecture, what we're trying to support. The other, well, we're going to walk through a couple of key takeaways, but the next one is really to highlight the fact that OpenHPC is a building block repository. And fundamentally, what we are doing is we're providing a number of pre-built ingredients that are common in HPC environments. And I'll show you the software that's available. But really, you can think of it as just a software repository. All right, and the way that we have designed our particular software repository is that it's compatible with standard Linux distro package managers. So on the SUSE side, what that means, if you've installed SLES, you can enable the OpenHPC repository and install a bunch of packages with Zypper. It's just natively using the package manager. And because it is very modular and it's building block oriented, we have a lot of software, but we may not have everything that you need. And so one of the things I like to remind people is that if we don't have the resource manager that is your favorite resource manager, it doesn't mean that you can't use OpenHPC. You can still leverage bits from OpenHPC, install your resource manager, and then install a bunch of other development tools on top of that. But really, this is kind of the important part, is that you can enable a repository. If your system is on the internet, it just installs right out of the box. If you are on an HPC system, yikes, I hope that was a balloon, or not something else. If you are on a system that doesn't have connectivity to the internet, which is certainly a possible configuration on an HPC system, one of the things that we do is also we provide a large tarball that you can download that has all of the packages in one particular tarball. You can unpack that, and you can enable the OpenHPC repository locally. You don't need any network connections at that point. So one of the things I just want to highlight here is that once you enable an OpenHPC repository, at that point you just use standard package semantics, but all of the interdependencies are managed for you from OpenHPC. And this is what we sort of know and expect from Linux distros, but we're also adopting that particular methodology in OpenHPC. So just as an example, here we're highlighting installing the Petsy library from OpenHPC. Petsy is a very popular linear algebra library. If you haven't used it in the past, but it's very popular. Has a bunch of linear algebra solvers. It has ODE solvers. It has optimization library. And what we're highlighting here is imagine that you want to install Petsy, but you want to install it for a particular compiler and MPI combination. So we want to install it for GNU 8 and MVAPage 2. So we're installing that on the top. And basically at that point, this is showing that we just had a vanilla SLES system installed, and it takes care of everything else. It installs the GNU 8 compilers, it installs MVAPage, and finally it installs Petsy, and all the other dependencies that go along with it. So the point here being that this just kind of works as you expect from a package manager. It's not much different than if you installed it from SLES directly. It just happens to be coming from a different repository. So another thing to highlight is we're very much in OpenHPC, we're very much fans of a hierarchical software environment. it's hard to know in advance which is your favorite compiler or which is your favorite MPI stack, right? And so if you've used a lot of production HPC resources, you know that they have a module system is very commonly used, and so we do the same thing. We take advantage of the LMOD modules implementation, but really the point from the OpenHPC side is that the designation of compiler and MPI variants is basically fundamental to everything that we do. It's fundamental in our build environment, our test environment, and also the way that we expose all of our packages from the end user environment. So this is just an example showing, imagine you installed OpenHPC, this is with a slightly older version, but you then look to see packages that were available. So this is highlighting, these are packages that I have loaded in my environment. So this is from an end user perspective, not root, but as just someone who wants to do some science. I have the GNU 7 package loaded, and because of that, if I look at all the software that's available, I can see that it's all compatible to be used with GNU 7. I also have mVapage loaded, so these are all parallel libraries that at this point were built with mVapage 2, and so I have a very self-consistent environment. The other thing that we do is we also know that it's very commonplace in HPC that you're going to have multiple versions of the same software installed, right? And so we sort of assume that that's going to be the case. We design that into our build environment, and so the thing I just want to highlight at the bottom here is this is a situation where we have two GCC compilers installed at the same time. So this one happens to be GCC 5. This is a newer version that we did later in OpenHPC releases, which is GCC 7, and they can coexist together, right? And that's a little bit outside of the norm of a standard Linux distro installation, but it's something that's so commonplace in HPC that we just make it a first-class citizen within OpenHPC. The other thing that we do is we make it such that if you wanted to use a different compiler or a different MPI stack, you could just switch and everything would be automatically reloaded to make sure that you have a consistent environment. So we're very big into this hierarchical software environment in OpenHPC. So that kind of focused on the package manager aspects of OpenHPC, but another key aspect of what we're doing is we provide a lot of validated recipes that people can use on bare metal systems. So in addition to just being a package repository, we have about 10 different recipes that you can follow. If you're starting up from scratch, where you just have a large cluster and you've installed SLES on a system, one of the things that you can do is go pick, you sort of choose your own adventure, and that's what we're trying to highlight here. So depending over here on the right-hand side of whether you had ARM or x86 systems, you could choose, but you would use the Werewolf provisioning system, and you could choose between Slurm and PBS Pro. And once you pick that combination, we would have an install guide for you, and basically it would provide all the instructions that you would need to actually stand up that cluster from bare metal, right? And the idea here is that we're providing a lot of different recipes, and that's probably a good thing to also appreciate from OpenHPC is that it's not just one way to do things. We understand that people have different preferences, right? Maybe you like Slurm, maybe you like PBS Pro, maybe you're doing the same thing on two different architectures. That's really freaking me out. On ARM and x86, and we actually provide recipes that we spend a lot of time validating these recipes. So every time we do a release, we actually run through all of our recipes in a continuous integration environment, and we actually do bare metal cluster installs every time. So in fact, our systems that we have housed at the Texas Advanced Computing Center, we've installed these poor little nodes. We've built something like, I don't know, 4,000 or 5,000 clusters over the lifespan of the OpenHPC project. So we have about, as I said, about 10, and the latest versions are always available on our GitHub site. But these are also a good thing to learn if you're not super confident in doing basic Linux administration, for example. These have a lot of information about how do you start from scratch, how do you install packages, how do you do provisioning, how do you set up networking, how do you get InfiniBand going, all that kind of stuff. They're a good resource for just sort of learning about doing basic HPC system administration. So another thing that I like to highlight from the community aspect is one of the things we do is we spend a lot of time on providing consistent user environments. So I mentioned we're very big into this hierarchical user environment, and because we're doing builds across multiple architectures, what that means is that you can actually get basically the same software environment on two different architectures. So the ones that we're building on today, we do builds against x86 and ARM, and we do that, you know, for SLES 12 today. So we do builds for SLES on both of these architectures. And the point that I just want to hammer home is that you could basically install on two different architectures, install packages from OpenHPC, and from the end user perspective, it looks the same. So I'm just running module avail, and you can see that the same software is available from your if you're supporting users on your systems, they see no difference. It just happens to be a different architecture. So we see that as one of the benefits that OpenHPC can provide a really consistent development environment, number one, across multiple architectures and also across multiple distros. Okay, so that's kind of key takeaways. The next thing I just want to highlight is our latest release. Like everybody, we do a release right before Supercomputing, so we did something basically about a week ago on November 19th. And this is all of the software that's currently available in OpenHPC. I've highlighted, obviously, SLES. So what we tend to do in OpenHPC is basically we go with the latest version of the upstream distro version. That's actually what we build and test against. So currently on the SLES side, we're building and testing against SLES 12 Service Pack 4. As I mentioned, we have builds for 2 different architectures, and then this is all the software. So starting at the top, these are kind of administrative packages. If you happen to be just a scientist who's writing their own code, probably you care more about the things that start with numerical and scientific libraries. You can see we have a lot of libraries included in OpenHPC, a lot of linear algebra, a lot of BLAS, different runtime environments that we all see here. We have different I/O libraries, so we're supporting HDF5 and NetCDF, including the parallel versions of both of those. We have multiple compiler families. One thing I should probably say about this that's a little bit interesting. So obviously, we have an open source version end-to-end for everything. You can download OpenHPC completely zero charge for anything, and it can be 100% open source. But we also know that if you're standing up an HPC system, it's likely that you're going to also be using the vendor's compiler library as well. So for example, on the x86 side, it's certainly very commonplace that you might also install the Intel parallel compiler. So we're aware, we certainly understand that and we expect that. So one of the things that we do in OpenHPC, which is why you see Intel NPI here and Intel Parallel Studio, we can't ship those, but one of the things we can do is we can build all of this open source software that is pre-linked against the Intel Parallel tools. And what we provide in OpenHPC is we provide a compatibility package that if you go obtain Parallel Studio yourself, you can install the compatibility package, and then you can get builds of all this software that is pre-linked against the Intel compiler. And that includes the math kernel library. So, if you're very sensitive to performance, which a lot of us are on HPC, this is a good pathway to get access to Petsy, for example, that's pre-linked against the MKL library. And actually, one of the things we're working on right now is also do the same thing in the ARM ecosystem. So ARM has their own proprietary compiler, and so we're working on doing builds with the ARM HPC ecosystem as well. And that'll be available for SLES too. So we tend to add software over time. One of the recent things that we added here was the Osu Benchmarks. That was highlighted here. Basically, because we do all the hierarchical builds associated with this, if you take all this software and you add up all the RPMs, it's about 700 RPMs today that are available in OpenHPC for the x86 architecture. All right, so hopefully this looked like a decent list, but if you see that your favorite software package is not here, you might ask, how do we get additional software into OpenHPC? And at this point, because OpenHPC has been in existence for a few years, we really take community input on this, trying to decide what's the next things to work on. So we have a very simple submission site where anybody can request new software to come in. You don't have to be associated with the project at all. Here's the URL. But basically, this is how we have been responding to the community. So all of the software that you see here that's now in OpenHPC, all of this came in because people requested it for us. And we tend to we have an open call basically every quarter. Our next deadline is December 2nd. So I just mention it here because if there's software that you see that you think is important for your user base, you might want to consider requesting it, and we'll take a look at it. We have a technical steering committee that reviews this basically every quarter. And it's a lightweight submission process. It should only take you 5 or 10 minutes to complete. And you can see we really do, this is how new software finds its way. So as opposed to just asking me if we could add something, this is the way to do it. Go through this process. So the last thing I just want to highlight here in terms of what we're working on next, we are working on a major new release for OpenHPC. Today we're at OpenHPC 1.3.9. We've been on the 1.3 tree for a long time, and that's basically been supporting SLES 12 and CentOS 7. That's what we've been supporting. What we're working on, for OpenHPC 2.0 is introducing major new distro versions. So on the SLES side, what that means is support for Leap 15.1. And one of the things that we're going to switch towards on the SLES side is as opposed to doing our builds against SLES say 15, we're going to be doing against Leap 15, and that's because there's 100% compatibility between Leap and SLES. So we'll be using the completely open source version of Leap, so that's a big change for us. Other potential items of interest, I think I'm kind of already alluded to this. We're going to be doing builds against the ARM-HPC packages. We're going to be updating some of our build infrastructure so that you can support localized customization. You know, one of the things that's a challenge if you're doing lots of binary builds for folks, you sort of have to pick the least common denominator from a processor point of view. But some people, they want to sort of enable every whiz-bang optimization for a particular package. And so we're going to try to make that easier, that you can download a source RPM, and if you happen to be on, you know, Skylake and you want to turn on all the AVX 512 options, for example, we'll make it easy for you to do that. Some other things that are coming down the pipe. Today we're on Slurm 18. We'll be updating to the Slurm 19 tree. We're also on GCC 8. We're going to be going to GCC 9, so all of our future packages will be against that. So these are some things that are coming out in terms of timeline. We hope to have this available basically in the first quarter of 2020. And that's really it. And just a quick summary. You know, we've been around for a few years. We were formalized as a Linux Foundation project in 2016. It's a very active community. If anybody happens to, you know, be following us, we have a number of mailing lists. They're very active. I'm very pleased that everybody's really contributing and helping each other out. You know, I kind of focused on using these packages in a bare metal environment, but we have a lot of people who are also using these in a cloud environment. You obviously can pull them into a Docker container. We have multiple container environments in OpenHPC as well. That includes Charlie Cloud and Singularity, but most of our installation recipes today are targeting bare metal. We do have, we're thinking about actually providing cloud images. So for example, we'll probably be rolling that out first on EC2. And if you're interested in learning more about the project, we have a Birds of a Feather session tomorrow on Wednesday, basically at lunch. And I'd be happy to take any other questions if there are some. Yeah?
All right. You said you will take questions.
I would love to take questions. You can't hear, but I will take questions.
I don't think my mic's working. All right. Well, let's give it up for Dr. Schultz.
Thank you.
Thank you for coming to our booth and doing that again.
You're welcome.